Good morning, students. I hope everybody is doing well today. I'm feeling better than I was at the beginning of the week. This time of year is like the spring for me with the allergies and the all the stuff that blows in with all these nice hurricanes and tropical storms. But you know, it's fine. It's great to always have plenty of energy, but when I'm congested and stuff, then I lose my energy. So I'm glad that uh, I'm getting back kind of to the normal routine for Professor Ron. What we want to do today is to complete what we've been discussing with the inverse trig functions and do some computations with those, and then move into the unit circle again and talk about some arithmetic aspects that have to do with the abstract idea of an angle, and also how we can actually measure distance on the unit circle in an arbitrary fashion, and how we can actually compute some distances. So we'll also talk about some angular velocity too. So the topics will remind you of your high school geometry course, and also maybe some of your physics that you may have done in high school, where you talked about some circular motion. So what we want to do today is basically bridge the transition from the unit circle approach to trigonometry to the right triangle approach to trigonometry. Again, we're going to find that both of these just come together very easily, but we need to look at certain aspects of trigonometry a little bit differently to accommodate some of the ideas that we see with this approach that we're basically moving towards. So again, it's not always the case that we have to have several different ways to present something. We just want to be able to make sure that whatever methods we have, that they help us to solve the problems that get placed in our laps. And so that's what we try to do in trigonometry as we prepare for pre-calculus. Now, what I wanted to do, I kept saying the inverse sine, the inverse tangent, the inverse cosine, and the inverse secant are the four primary inverse trig functions we deal with. But I wanted to go ahead and share with you the other two, just so you would have them, not just to cloud the issue, but just to make you aware of them. You don't spend as much time with them, but you may encounter them. So I want to go ahead and share my screen. Let's see, I've got this other thing up. I'll get rid of that. All these different things we have on our screens starting to bug Professor Ron. Let me get my IPEVO up so you can see the screen. I had that closed down for my last class, I guess, to save energy. I save a whole lot of energy these days. So let me change the few of the settings. Sometimes students say that the document cam is a little on the dark side, and if it ever is, just let me know. I want it to be clean enough so you can see it, but I don't want it to be so light that it gets just flushed out. So here we go. Now, what I wanted to show you here, I just sketched this out to provide information about the inverse cotangent, just so you see that we do it the same way that we do the other inverse trig functions. And then we'll talk about the inverse cosecant. I just want you to be aware of them. Now, just like we had before, notice I've written all these with the -1 superscript, but I just want to remind you that you can also do the arc cotan. This is also a used version. Dr. Stewart uses this version primarily, and Dr. Larson uses this, but you will see these in the literature written in both of these formats. So I don't want you to think that if you see arc cotangent, that's something new to you. It's just the inverse cotangent function. So what we're going to do is look at this like we did before. Now, remember, when we start out the process, we start with the cotangent function, and then we want to look at a portion of it that's one-to-one. And so we go to the principal branch just like we did with our last class. And so we deal with the part that runs from the vertical asymptote x equals 0 to the vertical asymptote x equal pi. So now, just to kind of remind you, remember for the inverse tangent, we were at this portion with these vertical asymptotes. So it's a similar procedure. And so again, we don't have the calculus here, but we know here, at least intuitively, that we have a decreasing function. So by restricting it, we have a one-to-one function. So we can define the inverse cotangent. So basically, this is the same thing. I just have some rules here that aren't going to make you as happy because this is not as nice a function as the inverse tangent. So I want you to be aware of that. So we'll say define the inverse cotangent as y equal inverse cotangent of x, or arc cotan. And then, of course, the domain becomes the range of the inverse function. So we would need x to lie between 0 and pi. Now, the interesting thing here, and again, I noticed that I made the correction here, but let me make it here too. Because the range is what we get here, all numbers. So I should have x from negative infinity to infinity. So the domain becomes the range, and the range becomes the domain. So I had it right here, but I didn't have it stated correctly here. So this means that we can input any x, so that's a little bit more flexible, just like we had for the tangent function. And another thing I did last class, just like the logs and the exponents, every time you have y equal inverse cotangent of x, you can always apply cotangent to each side and do the flip of it, which is cotangent of y equal x. So we can always think of the equivalent equation written with cotangent as opposed to inverse cotangent, just like we did with the base A logarithm and the base A exponential. And then, of course, the inverse equations, as we compose two functions that are inverses, we should get the identity. That's just basically by definition. So the cotangent of the inverse cotangent of x should give us x as long as we obey the definition of domain for the inverse cotangent, which is this guy here. So we've got this. And then if we flip it around, which is the more difficult problem, this is where we can have more variation in the x of cotangent. But if we want to write the inverse cotangent of x as x, x must live here between 0 and pi to respect the range of the inverse cotangent function, just like the range of the inverse cosine, which this mimics, except it doesn't include the 0 and the pi. Now, just with that, I want to share with you again the inverse cotangent of the negative argument. This is very similar to what you see for the inverse cosine and the inverse secant. We get inverse cotangent of the negative x is pi minus cotangent of x, because this is not an odd function. It's not even clearly. And so we have to make this adjustment when we have the inverse cotangent of a negative x. So, okay. And then just like with the inverse secant, you don't have an inverse secant key on your computer or on your Google calculator. So we have the reciprocal rules. Now, these aren't as user-friendly, and you probably won't ever really need to use these because you'll just be contented with other types of functions. But if they do come in to your plate, the inverse cotangent of x, as long as x is positive and we're over here, we can use inverse tangent of 1 over x, because this is compatible with the inverse tangent function. But it's not for this part because of the fact that the inverse tangent's running this way as opposed to up here. So we have to make an adjustment. So when we do the inverse cotangent of x for x less than 0, we have to do pi plus the inverse tangent of 1 over x. So this is not very user-friendly. Again, you may or may not need this later. It's just that like I say, in calculus, we don't do a whole lot of work with this. And that doesn't mean that I don't want you to at least be familiar with it and be familiar with its properties. So when we focus on the test and all, we'll do those 4 that I mentioned earlier that we did with the last class. But I don't want to discriminate against the inverse cotangent and then just like, well, you know, Professor Ron didn't think that was very important. I want you to see it because basically it's the same construct as the other ones. Now, let's just go ahead and look at the inverse cosecant. And it's a really nice function. It's nicer than the inverse secant when we set it up. So let's just do that one from scratch. So here, we'll say, so this will be the last one, 6, inverse, I'm gonna slide this over a little bit, inverse cosecant. So now you're thinking, all right, how are we going to restrict this? Well, we're going to do the same thing pretty much that we did with the inverse secant. We're starting with the secant function. So we'll say, just like we did before, we'll start with y equal cosecant x. And let me get another c in here before I put the x down. And we're thinking about where does x need to live? Well, before I fill this in, let's just go ahead and draw a principal set of branches. Remember, these are in 2 pieces, but we're gonna pick a decreasing part, and this actually is somewhat universal, but like the inverse secant, there's still some, you know, issues about how we define this. So remember, with the cosecant function, remember this is 1 over, we don't work with this as much, 1 over sine x. And so the zeros, or the vertical asymptotes, are at x equals 0. And then of course we have 1 over here, but we won't have to go that far. But we'll be into this branch, this is x equal pi. And then of course we'll have the negative pi over 2 and the negative pi. So we have x equal negative pi. Now what we want to do is include or utilize the negative branches. So first we'll go over here and we'll just say that the cosecant of pi over 2, that's 1. And then of course it blows up positively here. So let me just draw this. That's that piece, which is decreasing. And we want the same piece over here, so we're going to get a nice origin symmetric function. So cosecant of negative pi over 2 will be negative 1. So if you want to mark this off as a 1, and then here a negative 1, we get this. And then we can draw this part. So what we get are 2 branches that are symmetric. Let me give this a little bit more depth here. We get 2 branches that are decreasing, but symmetric relative to the origin. So you're like, oh, that's like the inverse tangent function. That's even better. So again, we're going to think of flipping the range in the domain to define the inverse cosecant function. But remember, this is y equal cosecant x. We're using x as the independent variable because we like that. And this is restricted, just like we had before. And so it's 1-to-1. Again, the calculus will verify that this is indeed a decreasing function, and the decreasing gives us the 1-to-1. So now we define, got to have the paper just right. That's what they call obsessive compulsive, but that's usually what defines a math professor. So define the inverse cosecant. And so we're going to say y equals, we can say arc cosecant. You can see why I'm not really a big fan of this, even though there are many mathematicians who like it. I just prefer the -1. So this will be inverse cosecant of x. And then, like we had before, the range becomes the domain. So the range here is from -infinity to -1 and 1 to infinity. So that becomes the new domain. So x living here. And then, of course, the new range is going to be from -π/2 to π/2 as long as we leave out 0. So now, of course, we can do this. I'll just go ahead and start writing this now. We can just say that cosecant of y equals x, doing an equivalent version of these two guys here. So then we have 1 cosecant of the inverse cosecant of x equals x, as long as we respect the domain of the inverse cosecant. So we have x living here. Now, like I said before, you can use the disjunction to write this with the absolute value. We use conjunctions a lot more than disjunctions, but that would be a more simple way if you use absolute value, your choice. And then 2, we can have, let's see here, let me set this a little bit. There we go. We have inverse cosecant of cosecant of x. Now this has more flexibility in it. When I do some computations, I'll show you how this works. So when we do the inverse here, this has to make sense in that x would have to be in the range of the inverse cosecant, which would now be between -π/2 and π/2. So if and only if x, so we'll do -π/2 to 0, excluding that. That's like the 0 to π/2 and π/2 to pi with the secant function. I'll remind you of that. So the construction's the same. So when we did the inverse secant, remember we had this one where we leave out the π/2. This was the increasing function. So same construction process. Here we have the decreasing function, but it's the situation relative to the origin is very good. So why is this an issue? Because the cosecant function is defined for a nice array of real numbers if we just throw out the multiples of pi. And so you can often find yourself with an x here that doesn't live in here. And if that's the case, then you have to make adjustments. And I'll show you how to do that, like with one of the first 4 that we have, but you could do it with this. Now, what's nice about this is that this is very user-friendly. We have the reciprocal rule, which is like the cosecant. This is inverse sine of 1/x. And then since the inverse cosecant is an odd function, it relates very well to negative inputs. Or if the negative accompanies the input, we can factor it. We don't have to do pi minus anything. So this is very user-friendly, like the inverse sine function and the inverse tangent function. So this is like really nice. So I'll say the reciprocal and the negative argument, I'll just say user-friendly, just like tangent. But the idea is it's often very useful to have this when we need approximations, if that ever arises. Again, it's like when I tell students you can use whatever function you like, as long as you can compute with it and do what you need to do. The upshot is that as long as the math is consistent, you're fine. So again, when we think about what we've already done, the first four you need to really commit to memory. These last two, you just kind of have in your back pocket to use if they ever come up. I won't really be focusing on these in this class, but I want you to be aware of them because the construction process is identical to the ones that we used for the previous four, okay? So that's the reason for that. I often don't take the time to do this with these functions, but I like to. It's good to have that. Now, I want to show you some computations that we can do with these functions. Now, when you think about the regular 6 trig functions and you think about how we compute with them, we have the unit circle. And if the value of t, which is the measurement along the unit circle for 1, 0, is written on the unit circle, then we can easily compute the value using the terminal point. So that's the definition of sine and cosine. So we're thinking we can do the same for the inverse trig functions with no problem. But again, symbolically, we can always represent the value of a sine or cosine function or inverse trig function just using the symbols and not maybe moving the calculation forward to an approximation. For instance, like when we need exact, like pi, we write the symbol pi. And we don't say 3.1416. We want exact, so we use the symbol for that. It's the same with the trig function. So don't forget that you've already been doing this. So don't think of it as being odd by any means. So let's look at an example. So for instance, let's just start back with something very simple. I'll focus on the inverse sine function first. So when we look at sine of pi over 6, we think, okay, that's the standard trig function sine. We have pi over 2 radians measured along the unit circle, and that takes us, we think of the terminal point, square root 3 over 2, 1/2. And we know that the sine of t is basically the y coordinate of the terminal point. T terminates at the measurement pi over 6 radians, and the terminal point y coordinate is 1/2. So we write 1/2. Now, just to remind ourselves, if we think about the inverse sine function, we remember that x lives between -1 and 1, and the inverse sine of x lives between negative pi over 2 and pi over 2. So it's the flip, basically, of the standard sine function. And again, we remember that the inverse sine is an odd function. So lots of times when you start to write anything having to do with computations of inverse trig functions, it's good to write everything down, especially if you're doing proofs, because this really guides you through the proof and you must respect all of this. If you don't, then your calculations won't make any sense and you'll just be making it up. So, like I said before, if we see that we're respecting the sine function, at least in terms of the inverse sine, we can also say equivalently that pi over 6 equals the inverse sine of 1/2. And of course, with the WebAssign, they give you all the parentheses and you close them. Never delete a parenthesis in WebAssign. Always use the parentheses unless you want to do the superscript powers, but be very careful to obey the parentheses. You can't ignore those. That's part of the computer algebra system. And so now you're thinking, oh, I see. I can think now of a reverse path. When I do the inverse sine, I'm basically thinking about a point on the unit circle, namely this point here, where the y coordinate is 1/2. There's only going to be one of them because we've defined it via a one-to-one function. And so then you're going to go reverse. You're going to go from the terminal point to the t measurement. You're going to go from the terminal point to the measurement along the unit circle. So we can see now that the inverse sine of 1/2 is just pi over 6. So again, it's the reverse path. So you already know how to compute these, at least when we're talking about values that we find on the unit circle. Now let's try another one. So you can play all kinds of trigonometric games going back and forth to convince yourself that you have a valid conclusion here. So now let's look at this. Inverse sine of the additive inverse of the square root of 3 over 2. Now, the reason I've given you the formulas for the trig functions of the negative arguments, or at least the arguments that have the additive inverse in them, is because they help you. The standard 6 trig functions have all of that. And you have that now for the inverse trig functions. So I want you to use it. So first, just to make the problem easier, we know that the sine function is odd, so the negative factors. So we see that the inverse sine of the negative root 3 over 2 is just the negative of the inverse sine of root 3 over 2. And so now, again, we're thinking, all right, well, let's just look at the terminal point where the y coordinate is square root of 3 over 2. Well, it's either in the first quadrant or the fourth quadrant. The fourth quadrant is the negative part. That's where the y is negative. So we avoid that. So we know we're at this point, 1/2 square root 3 over 2. But that corresponds to the t measurement of pi over 3. So again, just using the unit circle in the reverse path. So now this gives us the negative of pi over 3. Again, remember, negative pi over 3 lives in here, in the range of the inverse sine. So this is legitimate. So again, don't make it up. Write this down and just refresh your memory as, okay, how did Professor Ron write the definition of the inverse sine? How do we do this? And don't guess. You need to know this. And in some cases, students just remember the graph. They just remember the graph. And then the graph will encode everything you need to know. But everybody learns differently. Some of you might think, well, I'll remember the graph. I can see it better that way. Or I'm just going to remember this. I can work with this better. You choose. Or just know both. Well, if you know one, you know the other. But you know what I'm talking about. So now let's try another one. The thing about the inverse sines is that their domains are restrictive, at least for the inverse sine and inverse cosine. So say we had something like this. I'll just write this down. So if we look at this and we're thinking, oh, okay, well, the inverse sine is negative, so we're thinking about factoring the negative. But then we look at this and say, well, this really doesn't make a lot of sense to us, because if we evaluate the inverse sine, we know that the domain is restricted to this interval, -1 to 1. So we could start by factoring the negative, but then we're thinking that would mean that, you know, if we apply sine to both sides, we're now violating the range of the sine function. So we look at this and say, well, relative to our construction process, this is undefined. So if it doesn't make sense, we stop. Not a very interesting problem, so I won't do too many of them, but don't make it up. Again, if you know this doesn't have any mathematical sense. It's like saying, what's the natural log of -3? Well, that's undefined because that would violate the range of the base A exponential, which is a positive real number. So again, we're doing the same thing we've done before, just looks a little different. Now, let's try maybe inverse secant. Now, what do we know about inverse secant? Before I put the example down, let's just go ahead and refresh our memory with the inverse secant. It's like taking a grammar quiz in Spanish or French. You write down all the rules before you take the test so you won't forget them. When I was in high school, I used to do that with my French test. And I'd always make hundreds on the test, but my French teacher, Miss Cooley, Madame Cooley, she would always laugh and say, "Oh, you're just so meticulous." I said, "But Miss Cooley, I want to do well." And it paid off. I almost double majored in French, if you could believe it, because she was such a great teacher and she worked us. I got to Carolina and I started in intermediate French. So it's the same with math and music. If you love it, you just do it. So little tidbit there. So what about inverse secant? Where does x live? Well, we know it lives between 0 and pi if you throw out pi over 2. And then we're thinking, okay, well, that's the range. Sorry, I always want to do that. The second you write it, you're thinking, oh, that's the range, Professor Ron. So let me just write this here. So that's the range. And then, of course, the domain goes out this way with the disjunction. That's why you always write these down and just kind of in your mind think about the construction process. So now what was the range of the secant function becomes the domain of the inverse secant. What was the range of the secant function becomes the, what was the domain of the secant function becomes the range of the inverse secant function, but restricted. That's why this is kind of small, so to speak, at least in the interval sense. So now we're thinking, okay, what else do we have? Inverse secant of the negative angle is pi minus inverse secant of x, just reminding us what we did last class. And then, of course, we have the reciprocal rule. Let's go ahead and write all of this down. Inverse cosine, which we would find on our Google calculator. Okay, so we don't always have nice ways to approximate. Our calculators are fancy, but they're not that fancy. So we have this. So now let's look at an example of this. Let's start with a simple one. So I'll do inverse secant. I made up a couple here, square root 2. Now, everybody look at this and first convince yourself that this is actually defined. Square root of 2 is bigger than 1, and we go over here and we check by our construction process that certainly that lies here in this interval of the domain. So this is defined, okay? So we're starting simple. And again, if you want a picture, remember the picture of the inverse secant looks like this. Again, the range 0 to pi, excluding the pi over 2, and then the 1 to infinity and negative infinity to 1. So that's what we did last class. So you hopefully by now you have these on note cards, or if you don't, you're going to put them on tonight and get this learned. So now you're thinking, okay, well, this is good, no negatives. So we're going to go ahead and use the reciprocal rule. So this will be inverse cosecant of 1 over root 2. And so we're good because we're just having to work with the first quadrant. So you think over here in the first quadrant, 1 over root 2, we're looking for x values, and that's root 2 over 2, so that's right here. So that's the x value we're looking for. And if we go backwards, that's pi over 4. So that's just the first quadrant. So we get pi over 4. And we're done. So the idea here is we verify first, kind of like we did here. You know, we could look at this and say, okay, well, -2 is not in the domain of the inverse sign. So that's why that's undefined. But here we see that the square root of 2 is in the domain of the inverse secant function. Okay, so that's why this is good. Okay, again, not difficult if we just write it down. Just start writing and then put it together. You know, if you write something down and then you're like, I'm not sure what this was, think about the original function and then flip the range and domain and you're good. Now, here's another example. And you can do the same with the inverse tangent, but inverse tangent's easy. It's just so user-friendly. You'll be happier that we're doing this. So inverse secant, let's try this. -2 over root 3. Okay, so let's convince ourselves that this is well defined. Well, 2 is bigger than root 3. Okay, so -2 over root 3 is less than -1. So yes, it's in here on this side. So this is defined, okay? So now we're thinking, okay, how do we compute this? Well, now we can use our identity about the inverse secant of the -x. So we'll do that first. This will be pi minus inverse secant of 2 over root 3. So that's good. I mean, we're like, yeah, that's easy. That's easy to do. That's why I want you to use these. You know, I always thought when I started teaching, I developed honors courses in all of the classes, math classes that are taught at San Jac. And I kept looking in the books and saying, well, this is not enough. This doesn't give the kids enough to work with. They feel like they don't know anything. And so I would add additional items to make the computations more user-friendly. And then they said, oh, I'm seeing this is easier to work with. And so as I started teaching the honors with the regular sections, I let some of that stuff trickle down and say, well, you know, let me help my regular class students with the same ideas, not just say, okay, memorize this because that's all you can do. Well, that's nonsense. Everybody can learn math. And if you have the right tools, you can do anything you want. So it's actually, you know, even though I get criticized for being difficult, you're going to learn it correctly. So now we're thinking, okay, how do we do this? Well, now we go to the reciprocal rule. So this will be pi minus cosine inverse of root 3 over 2. And you're like, well, that's so easy. I can do this, Professor Ron. So now you go to your unit circle. This is in the first quadrant. What terminal point is this? Well, just write it down. This is going to be the root 3 over 2 1/2, and that corresponds to what? Pi over 6. So now you're done. So this will be pi minus pi over 6, which is 5 pi over 6. And so you don't have to guess. Lots of times, you know, I'll see students when we did in class, they just be punching around on some kind of fancy calculator. I go up to them and I say, put that away. I said, that's not going to help you. And of course, you know, they oh, you're a horrible person. I'm like, no, I'm not. I said, the calculator's not going to help you. It will not help you unless I ask you for an approximation. You have to be able to do this to understand what you're doing. So again, practice with this and you'll find that it's very, very doable. Now, I kept talking about the fact that, these inverse equations, how one particular example could be a little bit more confusing than maybe other examples. Let's just do a couple here, or just do one, and then I'll let you add it because I've got to get to the unit circle. So here's an example. Let's just remind ourselves of the inverse cosine function. What does that look like? Y equals inverse cosine. And then remember, like the inverse sine, x lives between -1 and 1. Just because it doesn't have any pi's in it doesn't mean that it's not real numbers. We like the pi's. The pi's are the pure measure. And then of course the inverse cosine is like the inverse secant. It lives between 0 and pi. That's why they're compatible the way we've constructed them. But of course the pi over 2 gets included here. So now, let me move Professor Ron over a little bit. There we go. So now we're thinking, well, what were the standard equations? So we had 1 cosine of inverse cosine of x equals x if and only if. Okay, so we have to respect what the domain of the inverse cosine, -1 to 1. And then 2 inverse cosine of cosine of x, which could be an issue for us, must respect the range of the inverse cosine, so x must live here. So these are not easy to remember if you don't know this part. So, and then of course, what was our the inverse cosine of the negative arguments? I've got these listed, so I'm sure not to miss anything. This will be pi minus the inverse cosine of x. Remember, it's not the tangent, the inverse tangent, the inverse sine, and the inverse cosecant are odd. The inverse secant, the inverse cosine, and the inverse cotangent are not. So they have this form. Okay, so just remember that. So now let's look at an example. We want to compute the following. Inverse cosine, I'll just throw in some negatives here. Cosine of -5 pi over 4. Okay, when you look at this, you're thinking, okay, well, let me run over to equation 2 right here and say, okay, I'm going to use this because, I'm all about getting through with this. And then you're like, well, 0 to pi, x does not live there. Okay, so I'm like, cannot use this. This makes perfect sense because cosine of this is defined. Cosine is defined for all real numbers. But if we want to use the inverse equation here, it's not going to work because that's out of the range of the inverse cosine. So what do we do? Well, we do what I've taught you to do. Let's just work it through. First, the cosine function is even, so it absorbs the negative. Now, when we look at this, we're thinking 5 pi over 4, where that goes to pi and then to plus pi over 4. So this takes us to the third quadrant. That's a third quadrant. And we love to move everything to the first quadrant because we're lazy. But remember, in the first quadrant, everything's positive. But in the third quadrant, the cosine is what? It's negative. It's less than 0. So we're going to do the reference number with the negative sign. So we have cosine inverse of the negative of cosine. And what's the reference number? That'll be 5 pi over 4. I'm doing this all linearly now, minus pi. So we need to remember our reference numbers. If you're in the third quadrant, you subtract pi from the value of t, and now it's a value of x. Doesn't matter what we call it. So now you're thinking, okay, well, we're good to go. This is inverse cosine of the negative of cosine of what? Pi over 4. Okay, so now we're thinking, oh, all right, so we've got the inverse cosine of a negative, so we can use the identity for the negative argument. So we can factor that. Well, we can't factor it, but we can write this. So this is pi minus inverse cosine of x. So again, there's the x. So that's what goes here. We've got the negative in this particular case. The thing is, when you think about what we're doing here and you think about how this works, I think you'll be fine. So let me go ahead and write down everything that we need here. So just a second. This is all of the x right here. So this is right, this negative, and this is the x right here. So I need to write that correctly. So we've got inverse cosine of cosine of pi over 4. Because that whole thing is the x. So now, if we look at this and say, okay, are we good to go here? Well, we know this is good because now we can go here and look right here and say, oh, okay, well, this fits here because x lives between, in this case, 0 and pi. That's a pi over 4. It lives right in there. So this will be pi. These will collapse and just give us x. And the x here, in this case, here's the x now. And that just gives us minus pi over 4. And then this equals 3 pi over 4. So the thing is that we have to respect the x's as we move through these computations. So remember, this allows us to deal with the negative as long as we make sure we keep the right x to give us this. And then now we can use this directly, which we couldn't use at the beginning because pi over 4 lives between 0 and pi. And so now we can see that the inverse cosine of the cosine of negative 5 pi over 4 is just 3 pi over 4, which lives in the range of the inverse cosine. That's how you do this problem. And that way you won't mess it up. And it all works because if you leave something out, the identity will tell you what you've left out. So as you work through the problems, don't make it up. Write down what you know about the inverse trig function, and then let the computation tell you how to do it. So again, notice, cosine is even, right here. Reference number, third quadrant, reference number, cosine in the third quadrant, negative. Okay, then we reduce this because, you know, what pi from 5 pi over 4 is pi over 4. Now we've got something that looks like we've got a negative here. We've got this, but now the x is all of that. So we get pi minus inverse cosine of the x, which is that. But that takes us right to here. Here, the pi over 4 lives in there, so we can just write x in this case, which is pi over 4. And then pi minus pi over 4, 3 pi over 4, and we're done. So that's how you execute these problems. Now, this is a hard problem. You won't find anything probably this difficult in the WebAssign, but if you can understand this problem, you can do any problem in the WebAssign. And I'm big on symbolic computation because that's exactly what you need to be able to do when you do the calculus. And so you need to study this problem. I made this up. I mean, I probably make up better problems than WebAssign, but WebAssign is so good because it gives you reinforcement. And for the most part, it makes you better. And I believe in it. Sometimes I'll say WebAssign is smarter than Professor Ron, but WebAssign is just a computer brain. And it's coded. And so if the coding's not right, WebAssign's not very, very popular, but most of the coding is very good. Okay, so now that's inverse trig functions, and maybe more than you wanted to know. I'm just joking, that's what you need to know. So now let's look at maybe the unit circle in a way that we haven't done before. That is, we're going to keep everything we know, but we're going to look at it for some new aspects that maybe we just haven't had much need to use at this point. So what I want you to do is let's go ahead and draw a circle. Okay, let's just draw a circle. We're going to draw the unit circle, and then we're going to draw some other circles. So let's just draw a unit circle, and we're going to define the new abstract concept. So this is going to be, these are going to be radius 1. So let's just go ahead and connect all of these. Yeah, that's pretty bad. Let me do that over. I'm not using this side, but it's still, I still have to stare at it. You go, that looks a little better. Still a Charlie Brown head, but that's okay. That's like my head. So now what we want to do is we're gonna think unit circle. So we're just gonna draw. We're going to start here at 1, 0, even though later on we're going to have an arbitrary section of the unit circle. And I'm just going to connect. Well, first, I'm going to do this. I'm going to take a distance along the unit circle from 1, 0, just like we've been thinking about measurement in a counterclockwise direction. This is going to be t. And then, of course, we're going to have the point, the terminal point here, xy. So cosine of t would be x, sine of t would be y. And now we're going to think of another abstract concept. Because when we get to triangles, this measurement along the unit circle may not be as useful. We can always impose a circle, but maybe we don't want to do that. So here, this is going to be a chord of the circle, or actually a radius of the circle of measurement 1. And what we're going to do is define what we call an angular distance. That is, and it's going to be very abstract. We're just going to call it t, which is the same as the t measurement from here to here along the circle. So what we want to do is we think of the angle t as a measurement of distance between two radii, well, radii, two radii of the unit circle. So this is S1. Now, when we talk about radii, we're thinking of them emanating from the same point. And that's back in high school geometry, you would call this the vertex of a triangle. But we mean to say that we have radii that emanate from the same point, and that defines what we call an angle or an angular distance. And then you're thinking, well, you know, I mean, do we measure it here? Do we measure it here? It doesn't matter. It doesn't matter. It really doesn't. And so it's very abstract. So we're thinking, we're going to call this measurement of this angle here, this so-called angle, as the measurement t, which is the distance along the unit circle from 1, 0 to the terminal point. So it's like, okay, so we take this angle that we've created with these two radii, and we basically intersect the radii with the circle as they touch, and we call this measurement. And then you're thinking, okay, So as long as we're on the unit circle, if this were pi over 4, I can call this angle measurement pi over 4. And then I'm thinking, all right, well, that might be fairly convenient for triangles since you don't really have circles on triangles unless you just impose them. So you're thinking, all right, well, okay, so if I live in the unit circle world, I'm fine. And you're like, mm-mm. So I could have pi over 2 from here to here would be pi over 2. From here to here would be pi. Okay, so maybe that would be a flat triangle. So you're thinking, well, that might be a good starting point, but what if I have an arbitrary triangle circle? That is, what if I have an arbitrary radius? So let's move to the next level. So let's consider this. This is a good starting point, but it's not the end of the story. Let's consider a circle of arbitrary radius. Arbitrary radius r. So let's draw another circle now, maybe a little bit bigger. So we're gonna devise a couple of formulas here. Okay, so we got another circle. Now what we want to do is just think of an arbitrary radius r, not necessarily 1, but any radius you like, maybe square root of 2, maybe 3, maybe, 1/2. And so what we want to do is do the same thing again, create another abstract angle by drawing another radius. So here's another copy of R right there, just like those are 1 and 1, this is R and R. And so now what we want to do is, again, mark off a distance along the unit circle. So this is like high school geometry. Geometry is such a nice course, a challenging course if it's done correctly. So this is S. We're gonna call this more abstractly. We're not going to call it T, we're going to call it S, which is the standard notation for length of the arc or arc length. That's the even in calculus, we use S. And now, instead of T, we're just going to use the Greek symbol theta for the angle. So we'll think angle theta. Now, again, we can think of, counterclockwise measurement of theta, like we have measurement counterclockwise of T, same thing. We're not going to get rid of any of that. That will all be the same. We're not changing any of that. But then we might be thinking, okay, well, whatever we come up with here. So for instance, we're thinking, okay, well, how do we, here we know what the deal is. We've got the unit circle, but if we know r and theta for an arbitrary circle, can we figure out the length of the arc? And you're thinking, well, we should be able to set up proportions. And then again, whatever we come up with here has to work here. So if we come up with the formula here, it must be consistent with the unit circle. So that's another problem. Just like when we define the inverse trig functions, we have to respect the 6 functions we've already defined. We can't make it up, because if they're not consistent, it's just hash. So what we want to do is say, okay, well, what if we went all the way around the circle? Just like if we go all the way around the unit circle, that's a distance 2 pi. But now, of course, if we use the definition of pi, if we have arbitrary radius and we go all the way around, that's 2 pi times r. So for I'll just say this, complete a complete traversal of the circle, the distance is 2 pi r. That is just the circumference. That's the circumference. I mean, this is really trigonometry and geometry just blend together here. And so then you're going to think, okay, so if I want to relate, the angle to the distance traveled, I can set up a proportion. So, okay, so if I have an angle of 2 pi radians, obviously I'm using radian measure, pure measure, I get a distance of 2 pi r. I'm just going to set up a proportion here. And then, of course, if I move an angular distance theta, I want a formula for S. So I'm just going to call it S for arc length. But now I've just got S, theta, and R, so I should be able to write S in terms of R and theta. But now, of course, the 2 pi's absorb. So we get 1 over R. Well, how simple. We wish everything were this easy. So now cross multiply, S equals R theta. So now it appears, just using basic constructs of the Euclidean circle, we can now define arc length about the circle as the product of the radius and the angular distance. Okay, well, let's look up here. If R is equal to 1, S equals theta. Well, that's right, because that's S and that's theta. They're equal. So, okay, we're good. I mean, at least we didn't go backwards. So, you know, everything doesn't have to be difficult. I mean, inverse trig functions are seemingly difficult because they're new. This is not new, so this is easier. But once you get used to the inverse trig functions, then they'll seem easy, just like the first time you did the Descartes rule of sines. Even though that proof is difficult, the use of it is not. So now you're thinking, all right, okay, Professor Ron, what's the next thing that you want us to do? Well, it would be advantageous to do the same thing we did here if we want to analyze the sector of a circle. So for instance, if we shaded this piece of pie, so to speak, this part of the circle. So basically the object or the area subtended by 2 radii and an arc is called a sector. So the area subtended by 2 radii and an arc create a sector. So the sector, so to speak, is just a piece of pie. And we were thinking, since I shaded it, maybe it would be convenient to be able to compute the area of a sector. And you're thinking, well, that's the same thing that we did here, because we know the area of a circle. So for instance, so this is the sector. So this is a sector. And so let A be the area of the sector. So we're going to do the same thing like we said, let S be arc length. So if we do this correctly, we should be able to write the area of the sector in terms of R and theta. And if we can't, we'd be kind of disturbed because we certainly could do it for this. So now let's use our knowledge of high school geometry. Even though the Greeks proved that the area of the circle is pi r squared, you can actually prove it with calculus. The Greeks were geniuses. They came up with all kinds of results that really, they had their own method of infinitesimals. that I guess was really their form of calculus even before it was invented. But they came up with everything before we did, so they were geniuses. So we have, okay, all the way around is 2 pi, and the area for the entire circle, that is, if our sector encompassed the entire circle, would be pi r squared. So that's using our knowledge of geometry. And therefore, we're thinking, okay, just like we did before, we have an arbitrary theta and an area A. So again, we have a proportion that has A, theta, and R in it. So we should be able to write a formula for area in terms of R and theta. So now the theta's absorbed. So we get 2 over R squared equals theta over A. And now, of course, if you cross multiply, you get R squared times theta divided by 2. And again, we have another formula that we basically got for free. So you probably already knew these from your high school geometry or from your high school pre-cal or whatever. If you already knew them, fine. If not, it doesn't matter. Now you know them. But here's what's important. This requires the radian measure. This is all done with radian measure. So we're going to come up with another way to measure angles and stuff, which will be called degrees, which is simple, but it will not be the pure measure that we need here. So theta measured in radians. Radians. We need pure measure that's based upon the unit circle. That is, the unit circle gives us the proper measurement, or the circle in general gives us the proper measurement of lengths. Pure measure, radian measure, built-in measure. So if you compute the arc length of a circle or a sector area, only use the pure measure of the radian. The degree is really a pure measure, but it's something we create. It's not the same. It's not intrinsic to the circle. We like it though. All right. So easy. Probably already know this. Put these on a note card. And then there's some nice examples that you can work on in WebAssign. They're easy. They're not even, like I say, after we do inverse trig functions the first time, everything else is just going to kind of go downhill in terms of difficulty. And this is an easy one, so enjoy. So now, before we move on to some examples here using the newfound formulas, I just want to go ahead and say, well, there's another way of measuring that has become popular in the world. And I'm sure you already know about it. I mean, let's think of it this way. If you went up to someone on the street and said, could you mark off a radian, could you mark off a angle of measure pi over 2 radians? Now, if they were in Professor Ron's pre-cal class or they were a STEM major, they say, oh, certainly, no problem. But then they might say, maybe the person is an electrician and they know their stuff, but they work in degrees and like, I can do that conversion. Or maybe the person is a PhD in Elizabethan literature. Well, I didn't study a lot of math in my doctoral program. Could you help me out a little bit? Or what? Could you mark off an angle of 90 degrees? Oh, yes, I can do that, Professor Ron. I know this. I was raised with this. Okay, so what I'm trying to say is that humans get together and they decide that there's another way to chop up the circle, at least in pieces that might be more user-friendly. And this has stuck, kind of like the English system of weights and measures. You know, we love pounds, we love, ounces, inches, feet, miles. We live for that. The metric system has not taken over the United States. It never will. But you go to Europe or any other place and everything's metric. So we would be the ones that would be lost. So I'm just saying the degrees kind of stuck. So here's what we're going to do. That's a little bit of humor, even though it's pretty bad. I won't quit my day job. So degree measure. So what we want to do is divide the circle into 360 pieces. And you're thinking, who came up with this number? I don't really know the history of this. Maybe you should look into that. And we're going to call these pieces degrees. Now, and we're going to usually denote them with an uppercase O. Now, this again is pure measure, but when we actually denote an angle measure, like we've described, like an angle measure of pi over 4 radians, we normally don't write radians. We just say theta equals pi over 4. Well, if we use degrees, we need to symbolize either write degrees or use the little uppercase O. But it's still a pure number. It's just that we will manufacture it differently. So now this implies that we would want 2 pi radians and 360 degrees to be our conversion factor. So if we have two pi radians, we would want this factor to be the conversion between the two types of units, just like we were doing before with the arc length and the area measurements. So again, the 2's will absorb and we get pi over 180. So this would imply, or equivalently, a theta in rads or radians would simply be, in this case, pi over 180 divided by theta measured in degrees, or theta measured in degrees would be 180 over pi times theta measured in radians. So you're thinking, what are all those other numbers on Professor Ron's unit circle? Where they're these? And you're thinking, oh, good, because nothing's changing. The terminal points are all the same. We're just going to replace the radian measure, the T values, with degrees. And all the symmetry will be the same. So once we learn the first quadrant, we get the second, the third, and the fourth for free. And then we're thinking, man, these numbers will be a whole lot easier than multiples of pi. So the beauty of the degrees, I think, is that we see that it's so simple compared to the radian measure with the pi's. And that's why it's stuck for so long. So for instance, let's just kind of work this backwards. Let's just try something here. What if we had, I don't know, say we had pi over 4 radians. And then we're thinking, this is pi over 4 radians, and we wanted to write this in terms of degrees. So we'd say theta. So let's just say this theta equals pi over 4. And so theta in degrees would be, well, let's just go over here. We've got what? Pi. Oh, we want to absorb the pi's. So we're going to have 180, this one, 180 over pi times pi over 4. Well, the pi's are going to absorb, but again, 2, that's going to be what, 90 over 2, and then 90 over 2 is 45. That'll be 45 with our little degree symbol. Even though it's a pure measure, we have to say 45 because otherwise we would look at that as 45 radians, which would be a lot of laps around the unit circle. That would have several multiples of 2 pi. So, 45, you think about like about, 6 or whatever, that's going to be between 7 and 8 multiples of 2 pi. So that's that would be needed here to distinguish. So we would look at this as 45 degrees being equivalent to pi over 4 radians. And then we're thinking, okay, all right, well, what about 0 radians? That would be 0 degrees. That's easy enough. So if theta equals 0, we have theta equals 0 degrees. Nothing to do there. 0 times 180 over pi is just 0. And then we're thinking, okay, well, this is just half of the unit circle. So if we double this, we should get what? 90 degrees. So if we say theta equal 90 degrees, that would just be 2 times pi over 4, which is pi over 2. So this implies we have pi over 2 as the equivalent of 90 degrees. Now let's look for, I don't know, pi over 6. So theta in degrees, you can go ahead and put DEG here if you want. This will be right here, 180 over pi times pi over 6. The pi's absorbed, and 6 into 180, that's going to be 30. And now, you know, we go 30, 60, 90. So basically, if we're thinking, okay, we've got this line here. Let's think about this. We've got the line here where we flip. So we've got 30, we've got 30, 30. Oh, okay. Well, this is going to divide. This is going to be a third of the distance from 0 to pi over 2. So 2/3 of the distance will be what? 60. So this implies, okay, well, that was easy enough. So pi equal pi over 3, or theta equal pi over 3 corresponds to theta in degrees of 60. So there we have it. So we've got what? 0, 30, 45, 60, and then 90. And that's it. So that's why you thought 45, 45, 90 right triangle, or 30, 60, 90 right triangle, which you did in high school or general math. And if you know, like I say, a lot of the tech majors will utilize this when they've got to do basic trigonometry for plumbing or electricity, because those crafts and those certifications require that you can work with circuitry and work with plumbing, where you design certain systems to fit into a space in a house that you're contracting with plumbing. So they've got to use a lot of trigonometry, and this is actually more useful to them. So now we can fill it in. So let's do it. I mean, we don't have to work very hard because, well, we don't really want to. I mean, if it's easy, we just keep it easy. We have to think too much anyway. So when it's simple, let's just ride the wave, so to speak. Okay. So now we're thinking, all right, well, let's just go ahead and mark all of this off. There's kind of halfway in between. That's the 45. And then we'll do the 30, 60, 90. So we've got the 0 degrees, or the 360, like the 0 and 2 pi. And then we have the third, we won't do the terminal points. You already know those. 45 degrees, 60 degrees, and then 90 degrees. And now we can just mark off using symmetry the other points. So now we'll just say, well, okay, that's 30. So 90 plus 30, that's 120. And then that's 45. So 90 plus 45 is 135. And then down to here, 60. So 90 plus 60 is 150. And then add another 30, we get to 180. So let's add 30, we get 210. So this, boy, this would have been nice. The radian measure is much more complicated than this, but we've used that more, so you're still more used to it. And then 45, that'll be 225, right? And then if we add 60 to 80, 180, that's what, 240. And then 90, 90, and 90, that's 270. Now add 30 to get from 270 to 300. And then 45, that gives us 315. And then, of course, 30 less than that, that's easy enough, 330. So there's the degree measure. And now you can see from Professor Ron's unit circle that these were already there. Like I told you, a student asked me in an online class, she said, Professor Ron, can you please put the degree measure on there? And I think I told you this. And I had to find the coding for this. It's on a flash drive that I thought I had just lost. And I found the coding and I just added by the terminal points, the degree measures. And yeah, so I use polar coordinates to graph this and to code it. And my coding is not very efficient. I mean, I looked at it and I said, well, Professor Ron, you're just having a good time. So it's not completely efficient, but it certainly works very nicely. And then of course I got lazy. Not lazy, I just got bored and I added the fill-in colors and stuff. So there was a time after grad school where I was just into coding in the LaTeX and I would just find things to do. And when I started working at San Jac, this was the first thing I did. And all my students think, well, now I guess if you go to Course Hero or the Chegg, where half of my stuff ends up anyway, even though it shouldn't be there, I think you'll probably find this. But that's okay. If my notes are helpful, and they will be, then that's fine. Maybe we'll get more students at San Jac. But be that as it may, we live in an information society, and as Dr. Phil always said, once you put it on the internet, it's there forever. And so, you know, when I see this unit circle, and I'm thinking, well, they don't have the latest version. They don't have the one with the degree measure. So I kind of chuckle about that. Now, so when you look at this, you're thinking, well, the thing that we did before, like, you know, you add 2 pi to an angle, then it's coterminal, so to speak. It has the trig values are the same for that. Now here you just add 360, right? So you can get coterminal angles just like you have coterminal angles in radian measure. So again, you know, the simplicity is already built in. There's nothing to do here. So we will find there'll be occasion when we're dealing with triangles when this degree measure is, of course, very, very useful. And it's up here. You were raised with this. The radian measure came afterward. That's why it's not as natural to you. But mathematically, the radian measure is intrinsic to the calculus and Euclidean geometry, and even non-Euclidean. I mean, we've done everything backwards. So the degree measure is just something we invented because I guess we're kind of feeble and we're thinking that, you know, it's better off if we make everything a little bit easier. But I'm okay with that. Ease is good. So now what we want to do is say a couple of things about some distance or motion along the unit circle, or actually any circle, not the unit circle. And so what I want to do, and this is what I was going to say, is going to remind you of physics. So we'll say motion along the circle. This is easy. And then, of course, there's a really nice problem about sector area, about the tethered cow, and where the tethered cow can graze. And one of my former honor students, Alonzo Casas, he is now in public health and was an excellent student. He really liked this problem, and I named the problem after him. I cited Alonzo's tethered cow. And so I said, that sounds like the name of a famous restaurant or something, like a steakhouse or something. But I always remember that. And like I say, you'll enjoy doing the problem. It just utilizes the area formula for the sector of a circle. So enjoy that problem. Now let's draw a circle. I'm just going to freehand this one. We'll see how good it looks. Probably not too good. You know when the curvature is too sharp. You'll learn about curvature in Calculus 3. So now what we can do is just think in general. So we have something like this. So we have an angle here. And we're thinking if we're measuring how the angle changes with respect to time. So we could take the angle measure and divide by some unit time, and maybe we have an apparatus that will rotate at a particular angular measure per unit time. So we say angular velocity. We just define it. Will just be the measurement of theta divided by some unit of time. So time, or t, will be a time measurement or time unit. So seconds or minutes or something, and we give it a nice symbol. We use the Greek omega. I use omega in nu a lot when I write my calculus, especially in Calculus 3. So that'll be angular measure. Now, again, this is what we just adopt. And so maybe you have a long playing record, maybe some friends have the old relics from the past where you had, turntables that played music. I know you all grew up with the computer, but maybe, you'd have 33 revolutions per minute, for the long playing record, and then the 45 and the 78. So that's all old stuff. So you might think, well, what about if we were just a little dot here moving along the circle and we wanted to do like time rate distance, like distance over time, as opposed to angular measure or angle measurement over time? What about a distance like a linear velocity? So this implies that linear velocity we can now think of as distance along the circle. So we're moving this way, something like that, would just be what? We'll call it v, the Greek nu, and that would just be the distance on the circle, which is the arc length s, divided by t. And so now we think, well, this is r theta, because we derived that. So this will just be r times theta over t. So this will just be r omega. So the linear velocity we can define to be r omega. That is s over t, or r omega if we're given angular velocity. So these are very simple constructs that very, if you've studied some physics, you've done this, and rotational motion is an interesting concept in physics. And of course, you've got moments of inertia and things of that, which you can do as you get into more calculus. So the idea here is that when you look at this problem, you're thinking, well, we can do some fun problems with this. And here's a Webasine problem. So it says we have a wheel diameter. A wheel diameter is 20 inches. And then it says compute distance traveled if the wheel revolves, so revolves 10,000 times without slipping. So we're not driving in the rain or the snow, so no slipping, no skidding. So we're going to do this in miles. Now, in miles. And sometimes WebAssign wants exact, but in this case, once you get the exact, they say use 2 decimal approximation. So this is like doing the problems you did with the radioactive decay and Newton law of cooling, growth and decay, where you get an exact answer and then use your Google calculator to approximate. Yeah, I should change it around in the future and just have you type the actual answer and just see how many students are using my methods. Might be somewhat eye-opening. So now, one thing that we notice here is that we've got revolves, so revolutions. So we can think of one revolution as corresponding to 2 pi radians. Or we can have a conversion factor like we have 360 degrees and 2 pi radians. We could say 2 pi radians per revolution as a conversion factor if we need that. So now we do. So now it says compute the distance traveled. So S equals R theta. Now, when we think about this, we're like, well, how can we rig this? Well, we've got what R, half of this is 10 inches. And then we've got, in this case, 10,000 revolutions. And we have 2 pi radians per revolution. So that'll give us the angle, lots of angles there, lots of lapping the unit circle, or just lapping the circle of radius 10, right? So that gives us the R theta that we need. But now we're not done. So this is kind of like a chemistry problem where you do unit dimensional analysis. And so we need to convert the inches to miles, and then we can see what we get. So now we'll have what? 12 inches, 1 foot, and then what? I don't know if the kids of the 21st century know this, what, 5,280 feet, maybe you do. That's 1 mile. So when you look at this and you think about this particular computation, all the coding is right here and the dimensions work fine. So once you know that the dimensions are fine, you can leave them out of the calculation and just reduce the numbers. So let's write everything down. So we have 10, we have 10,000, and then we have a 2 pi, and then we've got 12 times 5,280. So this is more symbolic computation like we did at the beginning of the class. So let's just see here. We've got the 10 gets absorbed here. So this will be a 10,000 times a 2 pi. And then we have a 12, and this will just be 528. Now we can go ahead and keep reducing. Notice here we can get rid of the 2, so this will just be a pi. And of course that'll be a 6 divided by 2. And here it looks like at least we've got a 4. So this is going to be what, a 1, and then a 12, that's a 3, and then an 8, that's a 2, and then 4 into here, that'll be what? So we've got what, a 2, 2, and then we've got a 20, so that's a 5 and 2 zeros, so 2,500. So we can keep reducing. We've got another 4, so we have pi over 6, and so 4 here, that'll be a 3, and a 12, another 3, and then let's see, what do we have here? So that's going to be a 25. So that's going to be what, 6, and then a 10. So that's a 2, and then a 20. So that's a 5, a 625. Right. So now, and then of course we've got the pi, and so 625 is what, 25 times 25, and that, of course, there are no fives in any of this. So this will be 625 pi. And then of course you can multiply this if you want. That'll be what, 18, and then a 198. So that would be 625 pi divided by 98 miles. So this would be exact. So now we can use our Google calculator. So let's see here. If I think I've got this up somewhere. Oh man, let me go find it. A second. I have to get rid of some of this stuff. It doesn't always see it. I don't get this. Crazy. So now let's see here. So here we go. Google. Cool. So now let's see what we get. So we get 625 times pi divided by 198. And this gives us this is approximately 9.9166. And of course, we'll round that to 2 decimals. So 9.92 miles. So good old Google calculator. So again, if WebAssign doesn't ask for an exact answer, of course, this is exact, which is what you want to get, and then you can do the approximation. So just like I said before, if any of these calculations say compute this, compute that, and there's no indication of any approximation, then you give an exact answer. If you need to use a pi, you use it. Don't approximate. If they don't say approximate to a certain decimal or whatever, or round or whatever, don't do it, because it will always be wrong. I mean, and I still don't understand why some of you don't get that. It is important to follow the directions. I mean, I have to follow the directions, kids. I'm not any different from you all. I have rules and regulations I have to follow. So please be careful with that. Don't just assume anything. It will tell you what to do. And I like that. I mean, it's going to make you better. Now, here's another example. I found this from the WebAssign too. You can just do problems all day long with this, and they're not, I mean, once you do a couple of them, they're not very interesting, you know, for too long, but they do give you a little good aspect of how you utilize the geometry of the circle to characterize motion that's circular. So here's another example. We have a car wheel has radius 13 inches, a nice prime number. And then we say it is rotating 800 revolutions per minute. So that's an angular velocity there. And then it says compute the speed. I mean, it's kind of dry. Compute the speed. Compute the speed. Think about this as our uniform motion problems with the circle. Compute the speed in miles per hour. Now again, when we think about this, we want speed, and that's just r omega. So we get to use, again, it's all right here, right there. So there should be no excuse when you do these problems. If you miss them, it's probably because you just didn't do your conversions correctly, or you approximated when WebAssign said not to. Well, they didn't say not to, they just didn't tell you to approximate. See, that's where students are falling victim. They're saying, but it didn't tell me to give an exact answer. But see, that's the issue. Mathematics is exact. So if you give a mathematical answer, it is by definition exact. So don't read something into the problem that's not there. And I know I preach this to you all, and maybe I don't need to as much, but share this with all the masses who seem to think differently. So now we've got V equals R omega. Well, R is 13 inches. And then omega is what? 800 revolutions per minute. But we need to introduce some distance. So now we say 2 pi radians per revolution. So this is easy and it's kind of fun. So once we get all the dimensions in check, ladies and gentlemen, then we can say, okay, let's retire all the dimensions and just work with the numbers. And in this case, we want exact. There is no indication for any approximation. So this means exact. So our answer must contain a pi. Okay, so remember that. Now we need miles per hour, so that's a lot of fun. So let's convert to miles. So we have 12 inches, 1 foot, and then we have 5,280 feet in 1 mile. So that converts the inches to miles, and then we need just to convert the minutes to hours. So that won't be difficult. That's one conversion. So that's 60 minutes, 1 hour. Okay, so everything's good. Notice the inches are converted to miles, the feet absorb, all good, inches absorb, and then the minutes absorb, and we get hours. So the units are good. So units get a check. So now let's just go ahead and write down the numbers. So we have 13, 800. I'm using parentheses here to keep everything in good stead so we don't, sometimes dots are good, and I use those if we're doing a lot of prime factorization, but we're not doing that here as much. So I use parentheses, 2 pi. So boom, 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 and then down to 60. And then, of course, we've got our 12 and 5,280 like we had before. And so now if you want, we can go ahead and retire some zeros here. We can get rid of the 0 there. So this will be a 6 over 528. So this is checked off. We can just go it one by one. And then if you like, we can go ahead and retire the 2. So this will be a pi over 6. And then we have times a 13. I'm using little dots now, 800. So if you want, you can just do this. So now let's go ahead and reduce some more. We've got a 4 here like we had before. And let's see, let's see, did I get my 13? And then I had the 6 here. Just let me check everything. So I've got a 6, 5, 2, 8. And then I've got the 2, and then the pi, and then that becomes a 6. Those are going to absorb. And then I've got the 13 and the 800. Good deal. So now the 6 is absorbed. So we've got a pi. And now we're going to divide, and I'll write the 13. The 6 is absorbed, and we have 5, 2, 8. And let's see what we have here. Let's go ahead and divide by 4. So that's going to be a 1, a 3, and a 2. And then divide by 4, that's a 200. And now we can do another 4. So that's a pi times a 13, and that'll be a 50. And then another 4, that's going to be what? A 3 and a 12, a 33. And let's see, okay, we're good to go. So that's 3 times 11. There's not any more in that, so we're good. And so now we've got what? 5 times 3 is 15, plus a 1, that's 6. So 650 pi over 33. and the units would be miles per hour. So again, I was kind of surprised, but pleasantly surprised that when I looked at this, it said it didn't say anything about approximation. And I thought, well, that's good. That's just an exact calculation. And so that's how you have to type it. So if you have a calculation, let me give you one more example of that. I was going through the WebAssign problems and I saw some examples of things that would be kind of odd. So let me look at one of these. Where was it? It looked fairly interesting. Okay. Oh yeah, here we go. Here's one. Here's a WebAssign problem right here. That again was one of these ones where you actually were asked. It says in this case, it says find the area of the sector shown. So I'm going to draw it. And it says nothing about approximation. So here's one last example. Enjoy these problems. They're fun. Work them out, get a good answer. So for instance, here's another example of exact calculation. So we have a sector, compute sector area. Okay, so this will be what you'll be doing in the Alonzo's tethered cow problem. And here's what you're given in the problem. You're given a radius of 8 and 74 degrees. So basically, and then again, be sure if they highlight a certain portion of the figure that you're actually computing that. If they highlight an arc, then make sure you're finding the actual length of that arc and not the length of the arc that subtends the angle. You have to look at what they're asking you to do. Many students are falling victim to just making assumptions that aren't there. So now you're thinking, okay, well, area equals 1/2 r squared theta. Okay, well, we can do this 1/2 8 squared. And then, of course, 74 degrees is not in radians, so we need to do a conversion. So we have 74, and then we do 180, and then pi. So that will be the conversion to radian measure. So let's reduce this. So we have 1/2, and then we have 8 times 8. And then 180 here, we can go ahead and reduce a little bit. We've got what, let's gonna put the pi right there, and then the 74 over 180. So pi here, 2 into 8 will be a 4. And then we have an 8 here. And then we can write this as 10 times 18. And the 74 we can write in this case as 2. And that'll be what? A 3, a 37. So we get pi times 4 times 8. And now we can absorb. So this will be a 5, 37. And then we can write a 2 times a 9. So now the 5's stuck and the 9 is stuck, but the 2 will absorb into here. So we get a 2 pi times an 8 times a 37. The 2 absorbs. And then we got a 5 times a 9, which is a 45. So this will be 2 pi. And then we have an 8 times a 7, that's a 6 with a 5. So we have a 24, so that's a 296 divided by 45. So twice this, so that will be what? A 12, a 1, that's a 19 with a 1, 592 pi over 45. So that's what I mean by exact calculation. Now, again, what I'm finding is that students say, okay, well, you know, they went to their Google calculator and they gave an approximation and they say, I'm not, Professor Ron, I know how to do this. Why am I getting it wrong? I said, number one, how would you know how many decimals to type? And then when I ask them that, they're like, oh, I see what you're saying. Well, why didn't it tell me? And then again, I say, no. A mathematical response is assumed exact unless an approximation is requested. So again, when you look at a problem like this, if they say round, you get your exact answer and round and be happy with it. But if there's no indication as to how many decimals you need or what you would to write, how would you know? You don't know. And I think that's just a curse of just being slack in the education process. We're assuming that the exact answer is not preferred when of course it is, because it is devoid of round off error, which can plague calculations. If you ever take statistics, you'll know exactly what I'm talking about. And they say, oh, with statistics, you can make anything true. And maybe you can, but statistics is some very elegant use of mathematics. So now, what we have left, again, once we're done with this, we're going to move to the triangles. We're going to impose the triangles on the circle, and I think you're going to enjoy it. It will be easygoing, and then we'll try to push in a little bit with the inverse trig functions, how they relate with the triangles and how you can use triangles, and now the unit circle together. And then some of you will say, well, you know, I like using the unit circle. It's like, oh no, Professor Ron, I like those ratios of the sides of the triangle. That's so easy. I'm going to use that. So now you'll have many options as we work through chapter 6. And then of course, when we get to 7, it'll just be trig identity city and equations, which will complete our study of trig. So be very diligent in keeping all of this in your brain. Make your note cards, practice your inverse trig functions, and enjoy this, because the payoff, ladies and gentlemen, the payoff is ease in calculus. I remember a former student saying, Professor Ron's pre-calc class was hard, but he taught me what I needed to know and calculus was easy. And I believe him. And I know the student who said that, because every time in class he says, man, this is hard. But he kept saying, I know you're getting us ready for calculus. And he just said it was a breeze. Basically what he was saying is that you did not have to struggle when he got to calculus. When he saw trig functions, he didn't shriek. When he saw factoring and symbolic computation, he knew what to do. So you keep the good fight, keep working, and everybody stay well. I'm so happy that I'm back in the land of the living and I don't have the congestion. I don't know what I caught. It just must have been something blowing in the air, but I feel a lot better. And so I hope you all are doing well. Everybody have a good day. And if I don't see you at office hours, I'll see you next week. Bye.
Thank you. Goodbye.
Bye.
Thanks, everyone.
Thank you.
Bye.